And if you either asked in the worst possible order, or if you are dealing with an expert who is paranoid and doesn't want to be sued, you will get this. That's how a complete acyclic graph looks. Okay? And that one basically, notice interestingly enough, if you compute the number, it will be exactly 31, which is 32 minus 1. Right? 2 power 5 is 32. And if I give you 31 numbers, you can get the 32nd number. Okay? Right. So by this time, you should know arrows don't mean causality. If anybody tells you arrows in Bayes are for the causality, slap them. And don't sue me. Okay. So two things. This is the last thing that I want to mention before we end this class, I guess, for the first session, the non-extended session, is that in addition to providing this Bayes network, then you have to provide the CPTs, conditional probability tables. And you can reduce the number of numbers in the conditional probability tables by assuming specific types of conditional probability distributions. So if you have 10 parents, in the worst case, you need 2 power 10 numbers. But by assuming additional restrictions on the distribution, I can reduce the numbers I need. Okay? In particular, that should not be surprising at all, to actually provide, let's say, a distribution for continuous variable given a parent, you would need infinite number of numbers. But you never use infinite number of numbers. In fact, the first distributions you learned were things like normal distribution. How many numbers do you need for the normal distribution? You need the mean and you need the variance. That's it. And then it plugs it into a particular equation, an expression to compute the probability distribution. So normal distribution is an additional assumption over and above everything else you did. Do you see what I'm saying? So that's how you actually reduce the number of numbers. So first problem is joint distribution requires 2 power n numbers to specify, and those numbers are harder to assess. So we can use Bayes networks to reduce the numbers and just look at the conditional probability numbers that we need to get. But the problem there, next problem is conditional probability tables also can be very big if in fact the network is too dense. If nodes have too many parents, you're dead. Right? Because the size of the biggest conditional probability table is proportional to the node with the maximum number of parents. Okay? It turns out that you can reduce the number of parents if you happen to know that the parents are causing the parents are affecting the child in particular ways. For example, consider the following scenario. Your grade, which is a random variable. Your homework 1 score, homework 2 score, homework 3 score, homework 4 score, homework 5 score, homework 25 score, project 1 score, project 2 score, project 25 score, midterm 1 score, midterm 2 score, midterm 3 score, then reflection score, and other score, etc. Now this variable, just like you, has way too many parents. Do you see what I'm saying? To compute its conditional probability, imagine, I'll just assume maybe 15 assessments in this class. So I need 2 power 15 numbers. That's too many. But what if I were to tell you that your final grade is some sort of a weighted summation of all these numbers? Then I introduce this hidden variable called the sum variable. The sum variable depends on each of these guys. And your grade only depends on the sum. Do you see what I'm saying? All of a sudden, nobody has more than one parent. You just got see what just happened. Right? Is it without loss of generality? No. Whenever you say P equal to NP, it's never without loss of generality. The generality basically will be lost here because I said your grade only depends on the sum of all your assessments. If, for example, your grade depends on, it actually gives differential treatment to certain assessments more than other assessments. And there is no linear way of combining them. Then some variable is what you feel your grade depends on. I know better. Do you understand what I'm saying? Okay? So, to reduce the CPT size, if I have something like this, I can introduce a hidden variable such that you have a network like this. And you can easily see that it reduces the number of numbers you need, like hugely. Okay? The last one that I want to mention is even CPTs can be quite hard to specify. Given any number of parents that you have, you still have too many entries in the CPT table. In that case, you will do the trick like what normal distribution does, which says, I can compute the entries from just a few numbers. I don't need 2 power k numbers. So, that is the last one that I want to mention. Where am I? Yeah, this is what's called the noisy R distribution. And since it's Thanksgiving, we should end on the children shooting the Indians or vice versa. I don't know, I shouldn't have said that. I mean, but so imagine you happen to be lucky enough to be standing in front of a 15 people wielding guns trying to shoot you. This is what happens when you are being given a death sentence. Imagine that all of these guys are noisy shooters. In the sense, in addition to yelling while shooting, they actually miss once in a while. The real question would be, are their missing probabilities independent or dependent on each other? Do I look at my next guy to say, oh, that guy missed, let me do it now? No. Normally, how many of you have been in front of a shooting? Okay, there's still time, 2 weeks. But anyway, so the point is that if you have k people in the firing squad, okay, then and if k of them fire, you still living depends on all of them missing. If the probability each of them miss is, let's say, p, then the probability that all of them will miss will be p1 times p times p times p, 50, p power 50. If so, the probability that you'll actually die is every other case, which is 1 minus this. You see what I'm saying? This firing squad is what is captured by noisy R distribution. So, for example, essentially there can be multiple causes for fever. Cold, flu, and malaria can all cause fever, but they also cause it noisily. That means sometimes cold gives you fever, sometimes it doesn't. Sometimes malaria gives you fever, sometimes it doesn't. Sometimes, flu gives you fever, sometimes it doesn't. But their failure probabilities are independent. At which point, normally if I have 3 variables and fever, conditional probability table for fever, I would need 8 numbers. However, what I'm showing you here is I only need to have numbers, I only need to give you the numbers for the rows where only one of them is true. If malaria is true, you not getting fever is 0.1 probability. That means malaria missing you. Okay? And similarly, if flu is true, you not getting fever is 0.2. That's flu missing you. And if cold is true, you not getting fever is 0.6. That means that's cold missing you. Given these 3 numbers and the noisy R-ness of distribution, you can compute all of the numbers. Do you see what I'm saying? If, for example, if you consider something like this, flu and malaria are present, then for you not to get fever, both of them should fail, which is 0.2 times 0.1. Which means you getting fever is 1 minus that, 0.9. Now some of you think, I don't like multiplications, just give me more numbers. That's bosoness, because that will be requiring more assessment. It's like you can say, I don't like Normal distribution, it has exponential in it, It has mu, sigma, who knows, only Greeks know. I want my infinite table of numbers. Right? That's no good. Okay? So this is called Noisy-R distribution. Noisy-R is just like normal distribution. It is a compact distribution that makes certain additional assumptions about how things are connected here. So I will stop here for the regular session, take some more raspberry bars and gummies, and then we'll do the There's no conversion. They use both. They do. But again, it's a question of it's not clear that you need exact capture. For example, having more impedance, less impedance assumptions than the word is being sound. That is everything you assume is actually in the word, but not vice versa. Sound inference will never get so you can never go on gamma is very just inefficient when you
no, the that.
Okay. So what I'm going to do now is talk to you about inference in Bayes networks. It's itself a huge topic, but I want to at least start, and then depending on how it will go, we will continue next class, or I'll probably go to a different topic and give the rest of inference with some resources. But let me do this. So first of all, the good news is we start probabilistic inference with reduced expectations. In the following sense, assessment of satisfiability given a set of Boolean variables, in deterministic logic, checking whether or not there is a model for it. Okay, that's already NP complete. And you should not be at all surprised that probabilistic reasoning is harder, not easier. Because it not only, in a weird way, you can think of it this way. Given a probabilistic set of probabilistic variables, what you're trying to compute is number of models, not just one model. All the models in which the probabilistic constraints hold, essentially. That's what you want to think of. So it's not surprising at all that probabilistic inference is not going to be cheaper. It's essentially, in a way you can actually do this is to show, actually, if you are a theoretician, you can say that here is a satisfiability problem, it's a 3-SAT problem. Okay? And you can convert this 3-SAT problem into a Bayes network. Okay? Such that whether or not these 3-SAT clauses have a model is connected to whether this Bayes network, the AND variable, has true probability. You see what I'm saying? And so that basically tells you that Bayes network can capture an NP-hard problem, which means it at least NP-hard. Okay. Furthermore, but one of the interesting things essentially is that one of the interesting things essentially is that we basically can actually show, if you're into that, that it's what's called sharp P complete. The inference in probabilistic assessment is sharp P complete, which actually involves counting the models, not just finding one model, but counting the number of models for a set of classes. Okay? But there are easy cases. Just like logic has easy cases. Remember, Horn class logic was cheaper than full logic. Okay? For you, the cheap case for you winds up in the Bayes networks. The cheap case happens to be essentially any network that's what's called singly connected. A singly connected network is a network where there is at most one path between any pair of nodes in the graph. At most one path. Okay? So for example, this is singly connected. So is this singly connected. This, on the other hand, is not singly connected. Remember, this is a bad guy we saw, a couple of classes back. This guy is not singly connected. It's multiply connected. Okay? So it turns out that you can show that for singly connected networks, exact inference is polynomial. For multiply connected networks, which is the other side, the total number of networks minus multiply connected networks, where in a network is multiply connected if at least a pair of nodes has more than one path. It's not that every pair has more than one path. At least one pair has more than one path. Singly connected means every pair has at most one path. Now the interesting thing is, thankfully the Barbary earthquake scenario that we saw is singly connected. This one is also singly connected. What was this, by the way? Markov chain. Markov chains, you work a lot with Markov chains because they're actually easy to do inference. Just like Prolog uses Horn class logic. Okay? How about these? That network. Is that singly connected or multiply connected? And what is it? Hidden Markov model. Once again, there is a reason why people always look for lost keys under the light, because that's where the light is. It's not that the world is made up of hidden Markov models and Markov chains. It is that they are easier to solve. So you just hope that it's a Markov chain. You hope that it's a hidden Markov model. Do you understand what I'm saying? Okay? So not surprisingly, it turns out that all of these would be singly connected networks, right? The other one, on the other side, of course, this one is a bad guy. This is a multiply connected network, because at least there is two nodes, cloudy and wet grass, which has more than one path. And in those cases, it can be shown that it's not polynomial anymore. There exist at least some multiply connected networks which require exponential amount of computation to compute the probability, to compute the probabilities. Okay. Now here's the tricky thing. Since it's late in the night, late in the evening, I'll tell you how to convert P to NP or NP to P. Which is, if this is not polynomial, right? This is what your problem is. So I will essentially merge those two nodes, sprinkle and rain, and sprinklers and rain, to this node called sprinklers plus rain node. If these guys can take true, false, and this can take true, false values, this takes 4 values: true, false, true, true, false, 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 true. And furthermore, I can, if I know the CPTs for this network, I can get the CPTs for this network directly without asking any more questions. So did I just show P equal to NP? Because this one is singly connected. You understand what I'm saying? This one is singly connected, and I told you singly connected networks are polynomial. And I just took a multiply connected network, which is a bad thing, and converted it a good thing. It's like connection conversion. What happened? Why haven't I proved P equal to NP? I mean, for computer science people, this is the stuff that you should check. Instead of those random proofs, they say 1 equal to 2, right? Or that the physics people will say, look, it never stops, it's perpetual motion. Okay, for computer science people, the equivalent is P equal to NP. If somebody says P equal to NP, since the Turing award hasn't yet been given out for that, you know that they're making up, and something went wrong somewhere. So what is the problem?
Combine exponentially many combine for the table for
So it's very important to understand that complexity is a function of input size. Complexity is a function of input size. Okay? Do you understand what I'm saying? If you can always take something which takes a 5 input and does exponential computation and convert it into something that takes 5 power 5 input and does polynomial computation. If you don't believe me, think of the following scenario. We told you MDPs are polynomial in number of states. MDP inference is polynomial in number of states, computing policies. And I also told you that PDL planning, which is really not capturing the MDP problem, it is not doing the stochastic planning, it's not doing arbitrary rewards, it's actually doing simple goals and deterministic planning. PDL planning, I told you, is p-space complete. How can the cheaper problem be harder than the harder problem? You see what I'm saying? What was the difference?
because it's large.
What was the difference? These are the questions you guys have to ask yourself. What is it? Yes, what is the input? Here, it's a number of states. Here, it's number of propositions. It's polynomial in the number of states. If I have n variables, n state variables, then the number of states will be 2 power n. Being polynomial in 2 power n is the same as being exponential in n. You see what I'm saying? And you guys are at the graduate level and the senior level. You guys should know these things. You understand what I'm saying? Life is not just plug and check. You need to understand why things are the way they are. Okay, because there are enough people who are doing plugging and checking by just seeing Udacity micro lectures. Okay, what's the difference? Why did you have to waste so much time to do this? Okay, so anyway, so basically when you combine this, you increase the input size. And so of course you are polynomial in this exponentially larger input size. In fact, you increase the input size exponentially. Because this table will be exponentially larger than these two tables. Okay? This is your perpetual motion machine for computer science. Okay? Fine. So you understood this first of all, that singly connected is easy, multiply connected is hard. But then I want to talk about inference tasks. In general, we have two kinds of, mostly the really kind of inference task that we will be looking at is give me posterior distribution of some variables given some evidence. That's pretty much the inference that we are interested in doing now. Okay, and you know at the minimum that you always have a zeroth method, which is given the Bayes network with the numbers, CPT numbers, you can write it into a joint distribution. And if I give you a joint distribution, you should be able to answer any probabilistic way. This is sort of like saying, if I give you a set of logical axioms, I can draw the truth table, I can write the truth table, from that I can compute the entailment. That, as far as the theory people are concerned, that's enough. For the mere mortals who want to get done before the world ends, you want to make it faster. In particular, if you have a network with like 1 million variables, and you're asking a query involving just 2 of them, in most cases, you should be able to answer that without looking at a joint distribution table that is 2 power million. Do you see what I'm saying? That's what inference is all about. So of this inference, we'll talk about 2 kinds of inferences. Exact inference, which you pretty much understand, and approximate inference that I sort of mentioned earlier, but hopefully we'll come back to Okay. In the case of exact inference, in essence, you're going to compute the part of the joint distribution that is needed to answer your query. That's it. So rather than compute the entire joint distribution and answer every query, you look at the query and only compute the the rows that are needed. You see what I'm saying? If you do that, you can save time, not surprisingly. And that's the first order, and that's this slide. And the second order, which we will get to after the first order, basically says not only do you just pick the piece of the joint distribution that is actually required, but even computing that, you might be repeating multiplications, you might be repeating computations. So if you ever computed something once, you remember it. It's called memoization. So that if you again need that same computation, you go look it up. After you do that memoization, then you get to the first good idea for Bayes network exact inference called variable elimination. Okay? But you see where it's going. You start, the simplest zeroth order idea is make the entire joint distribution and then just answer every query. Second is only compute the joint distribution part that I need. The third is do that more efficiently. Okay? Those are what we're going to just show you today. So again, our nice algorithm, a nice Berkeley earthquake alarm joint John and Mary Kali. And imagine I'm trying to compute this query. Distribution of burglary given John a card and Mary card. So the assumption here is capital letters means I want the distribution, the random variable. I want the entire distribution for the random variable. Since it's a Boolean, then I need for the probability for true, probability for false. Right? And then the evidence is always given exactly. So John called and Mary called. Those are the small letters. If John didn't call, if you happen to know that John didn't call, you would say not J. This much you understand. So I'm trying to compute this. Okay? So I'll use my rules, conditional probability distribution definition by saying it's nothing but PBJM by PJM. This much is right. And then, remember I spent some time on talking to you last class about Bayes rule, and I don't like the evidence part which is coming in the joint, the distribution, the probability of the evidence which is coming in the denominator. So I would rather assume 1 over that is equal to alpha. And then if I get the full distribution, it will be alpha times j and alpha times k would be the two numbers. So then I know the actual probability is to be alpha times j by alpha times j plus k. You see what I'm saying? So that's what I'll do. So I'll basically just assume that I will never really need to compute Jm. I can just, because I'm going to get the distribution for B, I'll just write this as alpha times P of capital B Jm. This is the trick that you should understand, because you know how to deal with this. Do you see this, right? Because you don't need PJM, because you're going to get probability B being true and probability B being false. You add them up, it must be 1. So if I get those two numbers to be 4 and 7, then the actual probabilities are 4 by 11 and 7 by 11. That's the alpha trick. Right? But I just assume that doable, so I write it that way. And so then I will say this is now nothing but, so I just need alpha times PBJM. Now, given this guy, I know how to compute the joint entries. Any given single joint entry, you can compute it. I showed you how to do that. Right? All I need is, can I right away read this up from the? No. Why? Because it's actually missing 2 of the variables. So I need to marginalize those 2 variables. The 2 variables that are missing are earthquake and alarm. So I put a sigma over earthquake and sigma over alarm of PBEAJM. This is just math, right? Of this particular expression, J and M are already given to you. E and A are going to be decided by the summation. You will consider A to be true ones, A to be false ones, E to be true ones, E to be false ones. This is a compact way of basically writing 4 numbers, summation of 4 numbers. You see this? And then you do this for b equal to true ones and b equal to false ones. Right? So at this point, now the joint distribution entries, this will be all joint distribution entries. So you know how to compute any of the joint distribution entries by just looking at that network, because you know how to use the local independence assertions. So in particular, suppose I write so PBJM will be equal to alpha times this summation of PBEAJM. That can be written as PBEAJM can be written essentially in the topological order in terms of PB, PE, PA given PE, PJ given A, PM given A. I didn't do anything magic. I just basically got you up to this point by saying this is how you compute any joint distribution. If you don't know anything else from Bayes networks, if I give you a Bayes network and ask you what is the joint distribution entry for one particular joint distribution entry, if you don't know how to compute this, you're basically sunk. But the moment you can do that, you know how to solve anything. Right? So notice that in this particular case, I actually just added up the set of the joint distribution entries that I needed to add up. Okay? And furthermore, one of the other things I can do is these two summations don't have to be done at the leftmost side. I can push the summation inside. This is computer science. Just like in logic, after logic it becomes computer science, which is how to do things efficiently. Okay? If you are doing this, then you can pull the summations inside. So notice, for example, the summation over A is no longer useful for these two entries because they don't depend on A. So I put this here. And I know these numbers because I can read them up from the network. This sort of reduces the amount of times you are essentially computing same thing. Okay? So you pulled in the summation. This is your first order idea. And you should be able to compute this into the actual numbers if I give you the CPTs. Okay? The second order idea that I only want to mention to you but won't go into too much detail is essentially that if you look at this guy, this last guy, that corresponds to this computational graph, this flow graph. I mean, I know the word computational graph was also used for the gradient computational graph. But old days we used to use computational graph to be just flow graphs. Okay? So the flow graph basically is saying what things are being added to what things and multiplied with what things to give what things. Right? And I would say this particular thing is this. Convince yourself of that.